Okay, let's talk about energy graphs and energy conservation. First of all, conservation means we're keeping everything. So that means we're not losing it. And right now we're going to ignore heat. Heat's commonly the thing that will rob us from energy, and we're going to ignore it. We'll add it back in later, but we'll start without it. So let's talk about a roller coaster. A familiar thing that even if you've never been on, you've seen them. And realize they do this, like that. And we'll just side view like that. At this point in time, what you have up here is potential energy. You have gravitational. You have stored potential energy up there. As you fall down this hill, at this point here, your UG is going down, but your K is going up. Down at this point, let's call this point 0. The nice thing about gravitational potential energy is we get to decide where 0 is going to be. We get to decide where our reference point is going to be. So we can use that point as 0. So at this point right here, what's happened now is your UG is equal to 0, because UG is M times G times H. Well, H is 0. So therefore, you don't have any potential energy right there. So therefore, K is equal to all of the energy you started with. Now we don't have any numbers in here, so we're just really doing it from a theoretical point. So at this point in time, and all a roller coaster really does is trade potential energy for kinetic energy. When you get back to this point, your UG is going up, but your K is going down. And that makes sense. As you roll back up this hill, you're going to slow down. You're slowing down because you're gaining height. Now, right now, we have no friction. Hey, friction creates heat. So right now, we're going to ignore this. This is a frictionless roller coaster, cooler than a normal roller coaster. Now, if I was to look at a graph, let's look at this point here. Let's look at this point here, and let's look at this point here. There's two different types of graphs we can do with this. First of all, we can do a pie graph. Go old school on you. If I had a pie graph right here, the pie graph would look like this, and it would be all UG. Now, let's say this is halfway up. Well, at halfway up, at this point, curve it over here a little bit, UG would be half, and K would be half. At this point here, it's all K. So it's no different than any pie graph you've seen before, in the fact that here it's half potential, half kinetic. Here it's all kinetic. Here it's all potential. And then it trades back and forth. So if this point here was, let's say, 1/4 of the height, then what you would have at this point here would be something like this. You would have 1/4 UG, and the rest would be K. So that's how a pie graph works. Now a bar graph would look very similar in the fact that you would have this. You'd have U and K. And let's do it at each point. U, K, U and K, U and K. Well, here, and so let's say this is 100% all the way across. This would be 0% all the way across. So obviously with your first one, you're all potential energy. At this point in time here, it would be half potential and half kinetic. At this point here, it's all kinetic. Now remember, I can only add up to 100% of whatever I started with. I need to move that up a little bit. I apologize for that. I can only add what I have at 100%. Now, if I'm at this point over here, well, 1/4 of it is potential, and 3/4 of it would be kinetic. I cannot gain energy. It's that simple. So this is kind of a way to kind of a housekeeping thing. Now, the other thing you can do, if you get rid of friction, let's at least discuss that possibility. If we include friction, so with friction, we're still going to have U plus K plus, and let's just call it thermal energy. That's still going to be conserved. The difference is, this is what we oftentimes think of as lost energy. In other words, it's not going to show up as either potential energy or kinetic energy. It's lost into heat, so it's not going to help me. So in reality, what happens is, as a roller coaster keeps going through its loops like this, what's going to happen is here it's all U. Here it's all K, but a tiny bit was lost due to friction. Friction creates heat. Just rub your hands together. So what's going to happen is, as it slides, in reality, it keeps slowing down. So let's say this had 1,000 units, let's say 1,000 joules of energy right here. Down here, maybe it's going to be 990 joules of energy. Here it's going to be 980 joules of energy. Here it's going to be 900 joules of energy. So now, if we draw our well, let's do a pie graph. Let's do this point. Let's do this point. Let's do this point, and let's do this point. Both of these 2 points, h is equal to 0. Let's say this h is equal to 1/2 total h. So what's going to happen now is, let's do pie graph first. Pie graph, pie graph, pie graph, pie graph. Oh, those are great circles. 1, 2, 3, and 4. Well, here it's all UG. That's right. Here it's all K, except 10 joules are missing. So what we're going to do is, those 10 joules, that's going to show up as thermal energy. So it's kind of lost on my system. The rest of it is going to be K. Now, when I get to this point, before we divided it directly in half, but now what's going to happen is this. I have a little bitty 20 joule window. That's thermal energy. Then the rest is going to be split between K and UG. Over here, I have no UG, but my thermal window is bigger. And then the rest is K. So that's kind of a way to do it. You could translate this easily into a bar graph, except now you're going to have U, K, and thermal. So here, let's say this is 100%. Let's go all the way across like we did before. All U. Now at this point, we have U, we have K, we have thermal right there. Well, we know that most of it is K, but not quite all of it. There's a little bit of thermal in there. So it looks like that. And then, of course, if I had this one here, again, U, K, thermal. The graphs are kind of just a way to keep track of it a little bit. Thermal is bigger than it was before. Once that thermal's gone, it's gone. And then the U and the K split what's left. This one, there's no U, so that's easy. U, K, thermal. Your thermal is bigger than it was before. Once that thermal's gone, you can't get it back. And then K. These two are going to add up to 100%. These three are going to add up to 100%. These two are going to add up to 100%. So energy is still there. It's just turned into a different form. Hope this helped.